get started. So just gonna recap some stuff, but mostly what we did last class was the big proof on our division algorithm for our fields, or for our polynomial rings where the coefficients come from fields. We had to do quite a bit of work. We broke it up into cases, and then within one of the cases, we had to do induction. Again, this is not a proof that you need to be able to like spit out and do yourself, but understanding the ideas behind them really is like where some of that learning is happening. And then also recognizing when can you use that theorem, why it's helpful is another piece of it. And really, we see a lot of consequences from this. So we got some corollaries that kind of give us some more information now. Again, remembering that the coefficients have to come from a field. If they come from an integral domain that's not a field, like Z6, I don't necessarily get this theorem. I don't have a nice way to factor things out, or maybe I don't have a unique way to do this, right? Because this theorem doesn't just tell us, here's how to write f as a product of g plus some remainder. It also says, here's some properties about your remainder. It has to have degree less than f. And this is the only way that you can do this. These are the only R and Q that will make this work when your coefficients come from your field here. Okay, so we did our big example, or our big proof here. And then some of these consequences we did actually see previously, but let's just remind ourselves that when you're dividing by something linear, but in particular something that looks like x minus a, immediately you know what the remainder has to be. It's going to be a constant polynomial, and it's going to be the output. If you think of this as a function now, it's going to be the output of what you get when you plug in a into your function. Right, so I can think of my polynomial as a function and then plug in a for all my x's, and I'll get something back inside of my field. Okay, so again, when the coefficients are coming from a field, I can apply my remainder or my division algorithm. And the fact that this is degree 1 is really giving me a lot of information on what the remainder can be. And then we plugged in and saw the remainder was going to be exactly a constant, and it was going to be the value that you got when you plugged in a into your function. Right. So now if I think about dividing x minus 1 and I want to think of what is the remainder, I don't have to do my long division now, or use my division algorithm. I immediately know what my remainder is. Here I'm just going to plug in 1, not minus 1, but 1. So it has to be of the form x minus a. So here the a would be 1. I plug in 1 here, I got back 9. And so I know my remainder is the constant polynomial 9. Right, and I know now I can write this big polynomial as x minus 1 times something plus 9. Right, so it gives us some information on here. The next big consequence that we got, I guess you call a theorem, is our factor theorem. Again, this is giving us more information on now about zeros of our polynomials. So thinking again as functions instead of as polynomials, when I plug in this value from my field, do I get the 0 element back out? So again, it turns out if your coefficients are coming from a field, you take a from f. It's going to be a root of your polynomial if and only if x minus a is a factor of that polynomial itself. Right, so this is really saying my remainder is going to equal 0 here. So I can write it as a product, and so really I can think of it being a factor here, where, right, some reminders, g is a factor of f in this specific polynomial ring. If I can find another polynomial here, so that I can write f as a product of g times something else, right? Just like how I think with my integers, the thing to be careful about is that it has to land inside that polynomial ring. I can't go outside of it, right? Just like with my integers, I say 3 is a factor of 6 because I can find another integer so that when I multiply them together, it gives me back 6. Right? So it's important that it's coming from the correct polynomial ring here. Okay, and so we went through our proof on this one. It wasn't too bad, and it was really just a consequence of the last corollary that we had that depended on our division algorithm. Okay, and then the last thing that we did was we started to do some long division. Really, I gave you a big piece here, Here we're working in particular with the coefficients coming from the rationals. And I told you that when you plug in one, you'll get back 0. So one is a root or one is a 0 of your polynomial. So this is immediately telling me that x minus 1 is a factor of f. And essentially our goal is going to be, how can I write f as a product of different polynomials until I can't factor any of the pieces further down, right? So the first step in doing that is deciding, how can I write f as x minus 1 times something? And then look at what's left over and decide, how can I factor that further down until it's the furthest I can do in when my coefficients come from the rationals, right? It's important where we live, because sometimes I can expand it and I can keep reducing and factoring further here. Okay, so, right, if I gave you the correct information, which we can always check by plugging in 1 to see if we actually get 0 back out, the remainder should give us back 0, right? And so whatever I get up here as my quotient, I know I can write f as this quotient times x minus 1. So it gives me somewhere to start to further factor out my polynomial. Okay, so I'm not going to go through all the steps that we did. I'm just going to continue on in the step that we were at, where we multiplied 2x cubed to this polynomial, and then subtracted. Or that's the step that we're on. We're going to subtract this whole thing, so I should be putting parentheses around this, so be careful with our minus sign. And then we're going to continue. We'll see what we get. We'll bring pieces down. And see what else we need to multiply x minus 1 to keep reducing this here. Okay, so here I'm going to get a 0x to the 4th, which we expected because we chose the specific 2x cubed, so that would happen. We'll notice that these are not the same powers. We got to be careful. I didn't put all of my placeholders. I didn't put a 0x cubed here. So really I should have brought the 0x cubed and it would have made it a little more obvious, but it's okay. I'll get both my terms showing up here. So I get a minus 3x squared. Oh, let me do the cubed one first. I'll get a positive 2x cubed. So I have my minus sign in the front. And then a minus 3x squared. So I really had a minus 3x squared, then minus 0 x squared for this polynomial here. Okay. And so again, we keep doing this procedure until we're down and have a degree that's right, less than 1 really, and really we should get remainder 0. Okay, so here, what do we want to choose to multiply our x minus 1? 2x squared. Okay, so I'll multiply both of my pieces here by 2x squared to give me a 2x cubed minus 2x squared, and I'm going to subtract. Again, my first terms cancel out on purpose, so that's how I chose what I was going to multiply by. And now this will end up being addition because I'm subtracting a minus, a negative. So I'll get a negative x squared here. Okay, we're almost done. I can bring my minus x. Okay, and here I'm going to multiply by a minus x to give you minus x squared plus x. Oh, we had a 2. Let's see. Oh no, this is okay. I thought my last terms were going to cancel and I would get a 0, which would be an issue because I have remainder 2, and I shouldn't get any remainder. I should get remainder 0 here. Okay, but when I do this, it turns this into a plus, so these cancel. It turns this into a minus, we got minus 2x. And now I bring down my 2, and I decide I need to multiply by minus 2. And when I do this, I get minus 2 plus 2. I'm subtracting the same thing from itself, so I get 0. So this is really my remainder. And this is my quotient here. So this is telling me I can write f of x as x minus 1 times my q But because my remainder is 0, I can just write it like this, right? Plus my 0, I really just exclude that piece. Okay, so it gave us, right, I started with a degree 7 polynomial. I was able to now factor it down to degree 1 times a degree 6. And the goal is to decide, can I go any further? Can I take this degree 6 polynomial and factor it out only using polynomials where the coefficients come from the rational numbers, right? If I can, I want to keep reducing. And I know that the only way I'm going to get, or I know one way that I can keep reducing is using linear terms, something like x minus a, and checking, is a 0 of this polynomial? Or if I had information like that, if I knew more zeros of that polynomial, I could keep going. But there's nothing that guarantees me that I can always reduce it down to just linear terms, right? Even with our real numbers that we're more comfortable with, we can reduce down to linear and what we call irreducible quadratics. So even there, we can't bring it down all the way down to linear. So we can't assume that we can always do this process. But when we have a 0, we know that we can pull out a linear term or a linear polynomial from this polynomial here. Okay, so our question here is, can we factor f anymore? And really, we're thinking inside of this specific, really asking, can I? My x minus 1, I really can't do anything further. Maybe I could have pulled out like a constant that they had in common. But the real work would have been to be able to factor out this bigger polynomial of degree 6 here. Okay, and this question, like the answer to it, not obvious, but it turns out that we can't reduce this anymore. We can't factor it anymore, only using coefficients from our rational numbers here. Okay, so here, surprisingly, the answer is no. And what we're going to do in our chapter 17, after we do a little bit more work here, is we're really going to study when can I factor more and when can I not factor more, right? And not being able to factor more is really saying it's an irreducible polynomial in whatever polynomial ring you're working in. So it's important that you know which ring you're working in to know if you can factor any further. And we'll see some nice connections between these irreducible polynomials and then doing my polynomial ring mod and ideal generated by this this irreducible polynomial. We'll see some nice facts about that quotient ring. And that quotient ring is really going to tell us things about the ideal itself or about the polynomial itself. And so there'll be some nice connections between the quotient ring and between the polynomial and it being irreducible or reducible here. But we'll go into a lot more detail with our chapter 17. Okay, but we do still get another consequence from our division algorithm, which has to do with the number of zeros that you'll have for a polynomial of degree n. So here we're excluding the 0 polynomial because that one we say has no degree. So we'll talk about why we want to exclude it because it doesn't fit this corollary either. But something that we want to talk about is multiplicity showing up in our corollary. So we want to make sure we understand what this means. So here I can talk about the multiplicity of my elements from my field. Okay. Or some polynomial inside my polynomial ring where I'm taking my coefficients from the same exact field here. Okay, so if I want to think about the multiplicity, really this is going to be of a 0 of my polynomial. Here we're going to think we know x minus a to the n is a factor of your polynomial. So if it's the biggest, it's saying if I do n plus 1 or anything bigger, it's no longer going to be a factor. So x minus a to the n plus 1, and really, an n is not a factor. Okay. So if I see something like, if I already write it out in my factored form, I can write something like this. Okay, I can think about 2. 2 here is going to be a 0 of my polynomial. And I see it's going to have multiplicity 3, right? Because I can write x minus 2. I'll see 3 times showing up in my factors and no more times, right? Because really I can't factor x minus 2 out of this term here, right? I could have written this as something like where this has a factor of 2, and I'd have to be careful to collect them all together. But really, we want to think, what's the biggest integer that's going to do this here, right? So really, when it's a 0 of the polynomial, I know it's going to show up at least once. And so I know at least my multiplicity will be 1 if it's a 0. If it's not a 0, then the biggest that'll make this work will be the power of 0 here. So if it's not a 0, the multiplicity will be 0. Really, you think it doesn't show up as a factor. If it is a 0, the multiplicity is at least once. And that x minus a will show up exactly that many times in its factorization. That's really how you can think of it. Okay. So our goal here is to show that a polynomial of degree n over a field is just saying the coefficients come from a field, has at most n zeros. So this is really telling you that the degree is telling you the maximum number of zeros. It doesn't tell you have exactly that many zeros, but it's saying if you have zeros, n is the biggest number of them that you'll find up to multiplicity. So here, if I just had this piece, this would give me a degree 3 polynomial, and I have 1 0 of degree 3. Right, so you really count all of your multiplicities. That 1 0 counted 3 times here because of this multiplicity here. Okay, so we're going to prove this statement again through induction on the degree of your polynomial. So on our n value here. What do you mean by the zeros? So we can think of our polynomials as functions. And if I can plug in that value into my polynomial and I get 0, then it's the 0 of that polynomial, or I can call it the root of that polynomial as well. I think we wrote it out explicitly earlier somewhere in all of this. I don't see it, but it should be written down somewhere here. Yep. Oh, maybe right here. Yeah, we talked about the roots and then the factors as well. Okay. Okay, again, we're going to do this, our induction on the degree of the polynomial we're working with. And again, as because we're saying it has degree n, it can't be the 0 polynomial. So I can't have constant polynomials, and I can't have degrees bigger than 0, but I can't have f be the 0 polynomial itself because I'm explicitly saying it's giving back some number n. Okay, so here we're going to do our base case, and the lowest degree that we can have is going to be 0. So degree 0 here. Oh, and this should have been on a different line. It's not base case, I ended up this step all at once. So we're going to do our base case first, prove it for this, and then use our inductive step, assume it on one level, and then show that it's true for the next level. Okay. 0, or our degree is 0. Immediately we know this is going to be a polynomial of degree 0. So it is about my constant polynomials as functions. I need to think, what happens when I plug in my values into these polynomials? What do I get back out? That same constant every single time. And because the constant itself is not zero, I'm never going to get zero back out. So for these constant polynomials that are not the zero polynomial, I have no zeros, no roots, which is exactly the degree that I have here. So I do have at most zero zeros because I have exactly zero. This is really confusing because I'm saying zero a bunch of times. I can say roots instead. I really have zero roots showing up here, and my corollary is asking me to show at most I have zero roots. Okay, so here, these polynomials have no zeros or roots. So the number of zeros or roots is less than or equal to n, which is 0 here. So it does actually satisfy. At most, I could have 0 roots, and I know I have exactly 0 roots, so it's okay. Okay, so now I actually do my inductive step. So I want to start with something of degree n, assume it worked for anything smaller, and show that it'll work for this specific level now. So here in my inductive step, I'm going to suppose I have a polynomial where my coefficients are coming from my field capital F with degree n. So degree of F is equal to n. And we're going to assume our statement is true for all polynomials with degree less than. Okay, technically, we're going to be using strong induction here because I don't necessarily know that I need my previous step. I might need other steps in between and not just the one right before. So I am really going to assume that for every degree less than it, that the statement does hold true here. Okay, so here we're going to suppose we have a 0. Okay. So let's suppose this element in my field is a 0 of the polynomial or a root. So when I plug it in, when I think of it as a function, I do get 0 back out. And let's say it has multiplicity k. Okay, so what this is telling me is that I can write f of x as x minus a to the k power times some other polynomial. To have multiplicity k means that x minus a to the k is a factor of f. And it's really the biggest one that will do this. K is the biggest number that will do this. So really I can get some more information about what my Q is able to be. But something that we can see here is because f is not the 0 polynomial, I know that this can't be 0, right? Because if one of them was 0, I'd get the 0 polynomial, but I'm starting with something of degree n, so I'm assuming I don't have my 0 polynomial here. Okay, so here, this is not the 0 polynomial. Okay, and because we're working with a field here, we're able to, this is an integral domain. We're able to talk about the degree of f in terms of the degree of the factors here. So here, since f is a field, so it's an integral domain, we know that the degree of f, which is n, is exactly the same as the degree of x minus a to the k times q. Okay, and I want to think if neither one of these is 0, I can just add up the degrees of both of these here. Okay, and here, what is the degree of the first polynomial we have showing up? Integral domain. But really, I need that to be able to think about what happens to the degrees of products. I can split them up and think of the sums instead. If it wasn't an integral domain, I don't know that this is going to work out. Right? If I had zero divisors, my degrees could actually go down. Okay, so because it's an integral domain, I can think of this product, the degree of the product, split it up, and I'll have an addition of the degrees. And so now I just need to think, what is the degree of this linear polynomial multiplied by itself k times? It's exactly k, right? The biggest term I'll have showing up is x to the k with leading coefficient 1 on that one. Here I'll get k plus the degree of q of x. Okay, so this is immediately telling me that k is either equal to n or it's less than n. Right? Because these are always going to give me back non-negative numbers, right? This is going to be less than or equal to k or to n. Okay, but this was only one zero that we looked at, and really we want to think about what are all the other zeros that we could have. And I really want that when I think about all the zeros I have and all the multiplicities, that it doesn't go past n. N is really the biggest that it could be here, including my multiplicities. Okay, so if f has no further zeros, then we're done. Because then f has exactly 1 0 with multiplicity k. So up to multiplicity, I have k zeros, which is less than or equal to n. So it does satisfy my corollary here. But now I need to think, what happens if I have more zeros? Let's say little b instead of little a was another 0. I need to think, how many more can I have? And what will the multiplicity there look like? I want to make sure that when I add it up, it's still less than n. Okay, so if b is some other element which is a 0, not equal to a, and maybe I'll write root here. So root of f still. Then I know when I plug in b, I should get back 0. But I have one nice way to write my f in this way. Right, I know I can write it as x minus a to the k times my q. Okay, but when I plug this in here, because b and a are not equal, this is not equal to 0, and something not equal to 0 to some power won't give me 0 back out. So I need to think, if this is not 0, then this had to have been 0. Why is it so here we're plugging in b for your x value into this equation here, into this one way that we wrote our function in terms of x minus a. So here, anytime I saw an x, I'm going to replace it with b. And the thing I want to notice is that I have a product equal to 0 in a field where this is not equal to 0, so this one has to be 0. So it's really saying if I have another 0, it comes from that q, right? That's the only option I have because it doesn't come from my x minus a part. So here I'll have q of b is equal to 0. And so b is a 0 or a root of q. But we know exactly what the degree of q has to be. Through this equation, I can just subtract by k. So I know the degree of q is going to be n minus k. And my k here is at least 1 because a is a 0. And so I have a polynomial of a smaller degree now. And so I can apply my inductive hypothesis on here. I know that the number of zeros I have here up to multiplicity is this number. At most, it's going to be n minus k. I can't go past the degree of that polynomial. So the number of zeros up to multiplicity of q is n minus q. And so when I think about all of the zeros of f, I know I have k zeros up to multiplicity for the number a, and all the remaining ones up to multiplicity have n minus k. So when I add them together, it tells me how many I have in total up to my multiplicity. And we'll see if I add k to this, I'll get back n. So it doesn't exceed the degree of my polynomial. Yeah.
Could n minus k be less than or equal to n?
So here, in this case, we're saying a is a 0, and so k has to be at least 1. Because the multiplicity of a 0 has to be at least 1, or else it doesn't show up as a factor. Right, so because this is at least 1, it is strictly less than here. Yeah. The number of zeros up to multiplicity of f is now going to be n minus k plus k, or n. Is up to this number. It's really saying this is the maximum number of zeros I have where I count all of my multiplicities here. So if 2 was a 0, but it had multiplicity 3, I would count 2 3 times. Right? Really the number of times it shows up as a factor is how many times I count that 0 here. So it's okay that we have big multiplicities here. This n is really catching all of it, not just the zeros, but really how many total zeros I have if I see it show up more than once here. Okay, questions on this one here? Again, this doesn't tell you have exactly the same number of roots as you have your degree, but it gives you a maximum. It gives you a cap. Now I know I have between 0 and n roots up to multiplicity for any one of my non-zero polynomials. For my 0 polynomial, this is much different. If I plug in any number into this function, if I think of my polynomial as a function, I always get 0 out, right? So I actually have as many zeros as I have elements in my field. So really we exclude that polynomial because it works the most different as all the rest of these here. Plus, depending on how you think about your degree of your 0 polynomial, you might say it doesn't exist or it's negative infinity. And right, this is not going to work out in the same nice way as the rest of our polynomials work. Okay. Great. There's a little typo here. There should be that we saw previously that for this polynomial ring, where even if the coefficients come from a field, the polynomial ring itself is not going to be a field. But the only units that you have in that polynomial ring are going to be your constant polynomials, where the constants are units from the coefficients. So here, if it's a field as your coefficients, all of the units are going to be the constant ones that are not the 0 polynomial, right? But that's excluding a bunch of other polynomials, so they don't all have their inverses. And so we know that these are never going to give us back fields themselves. The polynomial rings are not going to give us back fields. Okay. In particular, right, the specific polynomial here doesn't have a multiplicative inverse, so it doesn't give us back a field. But it does give us back an integral domain if f is an integral domain. Oh, excuse me, if f is a field, then I do know that my quotient ring is going to give me an integral domain. And I won't be able to multiply non-zero polynomials and get the 0 polynomial back out. Really, because this is going to give me back, because f is a field that's an integral domain, I can do my work with degrees of my products to see it's not, the degree is never going to go down unless I'm multiplying by my zero polynomial. So that's really what's helping me here, is that nice consequence that we had about degrees when we're multiplying our polynomials. Okay. It turns out that we actually have more structure on this polynomial ring that we didn't really study previously. And it's known as a principal ideal domain. It's actually really nice, the structure that these types of rings have. But it wasn't important to us to study all the types of principal ideal domains. So we're only going to study it in this specific case. But I can have other rings with this property. And so we'll look at what this means. And for short, we'll do PID, for principal ideal domain. So this is going to be, first we need to be an integral domain. So that's where the domain part comes from, principal ideal domain. And the principal ideal part is really saying that every ideal that you have is going to end up being principal, right? So every ideal that you have is going to be of this specific form for some A inside of your integral domain here, right? So it's an integral domain, has all the nice properties, commutative, unity, no zero divisors. And on top of that, you know exactly what all your ideals look like. All your ideals are going to be some multiples of A, some multiples of an element in your ring here. Right, so really you can think the ideals are generated by the single element by your A here. So these have really nice structure, and we've actually seen an example of a ring, an integral domain with this nice property, where we knew exactly what all of their ideals look like, and they were all principal. Can you guys think of one example here? And there should only be one that should be obvious. What integral domain do we know all of its ideals of, and that all look like this? The integers. Here for our integers, this is going to give me back a principal ideal domain. Since all of its ideals we know are of the form, we could either write it as n times e, or the one generated by n. Really, these are the same here. All the elements that show up in here are really multiples of n, right? And I can't have any other type of ideal. These are all the ideals that I have. This is really coming from thinking first, what are all the subgroups that I could have of Z if I just think of addition? They all have this one form, and I'll add this extra operation. They still have this nice form. Okay, so this is our nicest example. Usually it's really hard for us to know when we have principal ideal domains, which is why we didn't go into a lot of detail for these. But it turns out when your coefficients come from a field, that your polynomial rings are going to end up, actually, I want to be careful here. They don't always give you, we don't always get a principal ideal domain if it's not a field. But if it is a field, we do get this nice property here. Okay, so here, when I have my integers, which is an integral domain but not a field, it turns out that my polynomial ring is not going to be a principal ideal domain. And really what we're going to look at is this ideal generated by two elements, which again, we didn't do too much on, but we can talk about thoroughly what does this mean. This is going to end up being an ideal, and I can't write it as being generated by one element. So it's not going to be a principal ideal because I can't write it as generated from one single element here. So just finding one example of an ideal that's generated by more than one that can't be written in terms of one specific element is enough for me to say that my polynomial ring is not a PID, not a principal ideal domain. Okay, so here, every element of this so this is my polynomial ring where the coefficients come from C.
Yeah.
Yep, so all my polynomials with the coefficients are integers.
I was talking about the other one.
Yeah, so we'll talk about here. Really what I want to do is I want to think multiples of 2, multiples of x, and add them together. That's what this ring is going to look like. Instead of just being multiples of one of the elements, if I want both, I'm going to add them together. Yep. So here this would look like 2f plus x times g for f and g inside of your polynomial ring. Right. Previously, if I just wrote generated by 2, it would look like this. If it was just generated by x, it looked like this. But because I want really this to be the smallest ring that has both of them, I want to add these two together. Right, and really if I had 3 elements in there, I'd do the same process and add all those 3 pieces together, and that's what they would generally look like. Okay. So something that we'll notice here for this piece of it is what can we say about the constant term of just this part? Of just the x times the g, where g can be any polynomial. So here when I multiply, this is the polynomial x, which has 0 as its constant. This can have any constant that it wants. But when I multiply it, what should my new constant be? It'll be 0. So this one here is always going to have constant term 0. Okay. What can I say about the constant terms of this one here? It's going to be even. All of my constant terms for this one, it's going to be even. Okay, so if I add these together, what should my constant term look like? Still even, right? And even plus 0 is going to give me even back out. Okay, so here in this, and I'm not actually showing that this is an ideal, but it is. We can check that it has all the nice properties. Okay, but here in our ideal, each polynomial has even constant term. Okay, and what we're going to do is really show this by contradiction. We're going to assume this is a principal ideal, so I can write it as being generated by one element, and then come up with something that goes wrong, come up with our contradiction there. So by contradiction, assume you can write this as a principal ideal. It's being generated by one single polynomial that comes from our ring where the coefficients are in my integers here. Okay. So one nice thing that we have is in here, we have unity in our coefficients. We have 1. And so we're going to have unity in the polynomial ring as well, right? Just the constant polynomial where the constant is equal to 1 here. So here I can replace my f and my g's with 1s or with 0s. And I know those elements are going to be included inside of this ideal. So in particular, if I have this as 1 and this as 0, I know 2 will be in there. And if this is 0 and this is 1, I know x will be in there, right? So as soon as you have unity inside of your coefficients, then any ideal generated by elements, those elements always have to be in your ideal. Okay, so here, we're going to take the fact that 2 is in your polynomial, in your ideal. Okay, so this is saying, what about 2? How can I write 2 if I know it's inside there? What does it mean to be in an ideal generated by one element? Louder? All the things inside this ideal are multiples of p. So this is telling me I can write 2 as p times something else in my polynomial ring. So I can write this as p times, let's call this q, or some other polynomial q with coefficients in z. Okay, and what we're going to do is study the degree, bless you, study the degree of both my pieces here to tell me something about what p has to be. right? But here we know that the degree of a constant polynomial that's not 0 has degree 0. Okay, and this is going to be the same exact degree of this product. Okay, right, and neither one of these can be 0, or else it's telling me that 2 is equal to 0. That's technically true in Z2, right? But in this case, right, I know neither one of these can equal 0. Right, and because my coefficients are coming from an integral domain, and neither one of these is 0, I can split this up using my sum. So here, this is since, see, and I'll put ID for integral domain again. And P and Q don't equal 0. Then we know that this is exactly the degree of P plus the degree of Q. This doesn't leave us with many options. If I know that the sum of these non-negative numbers give me back 0, then both pieces have to be 0. Right? That's the only way I can add up my non-negative numbers to get 0 back out. Okay, so that's really telling me that the degree of P has to be 0. Let's see. They're the same. Yeah, really, I shouldn't be writing P of X unless I'm thinking of it as a function and I want to plug things in. The polynomials I really should just write as like F, G, and H, but kind of out of habit, I do put the X's in there. But if you write it in either way, I understand what you mean. And I do go kind of back and forth between these. Okay. Let's see. Why is this going to give us an issue here? Oh. So this is why. So here I need to have be a constant polynomial. So I can only be like I can think of as an integer here. And I need to be able to multiply it by something to give me back 2. So what would be my options here for what P could be? What integer can I multiply to give me back 2? What are my options here? Right, and really positive or negative here. So my only options are plus or minus 1, plus or minus 2. Okay, we'll notice that this is a unit. Actually, both of them are units. Plus or minus 1 are the only units inside of Z. So these are the units inside of the polynomial ring with coefficients in Z. And so if this was P, if P was either one of these, then I would get the whole polynomial ring back out. As soon as I have a unit or unity in there, I have the whole ring. Okay, but I know I only have things in here with an even constant term. So those are not options. Right. This ends up giving me that this guy equals the whole thing, which is not true. Okay, so we need to think, what would happen if these were plus or minus 2 instead? Okay, and decide why would that go wrong? Why do we get a contradiction regardless of which case that we're in here? Let's see. Right, and I think in either one of these cases, I don't think that we're going to get X inside of that ideal, even though we get X inside of this ideal here. So in this case, X would not be inside of this ideal, but X is inside of the one generated by 2nx. Right, so that would end up giving us an issue here. Yeah, okay. Right, so really what we're showing here is that for this specific polynomial ring, when the coefficients don't come from a field, I don't always get my ideals look like these principal ideals. I could have them look different. They could be generated by more than one thing instead. So in this particular case, we found an ideal that was generated by more than one thing that can't be generated by just one thing. And so this one in particular is an ideal, but not a principal. This is not generated by one element. And so this is enough for us to say that this polynomial ring is not a PID. As soon as you find an ideal that's not principal, it can't be a PID. Okay, so really is important, right? This was an integral domain. And if we step it up one more, if we turn it into a field, this will be enough. It will be enough for us to know exactly what all of our ideals are going to look like. And this is why we're going to study ideals just generated by one element, because it really gives us the full idea here of what our ideals will do. Okay, so that's what our theorem says. If the coefficients come from a field, then we do have a principal ideal domain for our polynomial ring. Okay, so now I know as soon as the coefficients are fields, all my ideals are going to look the same. They're all going to be principal generated by one single element, right? So it allows me to do more with my ideals because I know exactly what the structure of them have to look like. This is also giving me information about, right, my ideals for my ring are really the kernels that will show up in my ring homomorphisms. So I know whenever I have a ring homomorphism where one of these is my domain, I know exactly what my options are for my kernel. If my kernel looks like anything else, I don't actually have a ring homomorphism there. So it gives me information, not just about the ideals, but about kernels where this is a domain, because kernels and ideals are essentially the same thing. Okay, so we can get started on this proof. Actually, it's not too long here. And let's work this through. Right, so immediately, if I know that this is a field, then I know that the quotient ring itself is going to be an integral domain. Right, just by knowing where the coefficients are coming from, I know when I multiply non-zero elements, I can't get zero back out because of my nice property about my degrees when I'm multiplying ends up giving me addition there. So I can't go down in my degree. Okay, and so we're going to take some ideal inside of my polynomial ring. And we can think what happens if it's the trivial ideal and then what happens otherwise. So here, if it's the trivial ideal, I can think of it as being the principal ideal generated by zero. And so in that particular case, we're done, right? But our goal is going to be to show any other ideal that we have has to be generated by one specific element. In that one, we saw it was generated by zero, and the other ones, we're going to have to decide what it's going to be generated by. And it actually, we have a lot of options on what it could be. Again, just determined by the degree of the things that show up in there. Really, we're going to see that one that has the smallest degree, that's not the zero polynomial, is going to be a contender for the generator of that ideal. Okay, so here, if we have I is not the zero ideal, so there exists a G, and I'll just write G here, inside of my ideal, but take away zero. Okay, I know I have at least one other element that's not zero. Let's call it G. And we're going to do more. We're not just going to take any non-zero one. We're going to take one that has the smallest degree. So I could have multiple options. I could have a bunch of constant polynomials in there, and I just want to choose one of them. I don't care which one it is, but if it has the smallest degree, then it will be a contender for the generator for that ideal. And we're gonna let, again, the degree of G be the smallest, or be minimal, smallest of the degrees in I star. Again, excluding our zero, regardless of how you think of the definition for the degree of your zero polynomial, if it's negative infinity or if it doesn't exist, we just want to exclude that from the options. So we're going to look at this list of polynomials, and we're going to choose one polynomial that has the smallest degree. It could have degree 0, 1, or 2. All that's telling us is that any polynomial smaller degree can't be inside of our ideal. Okay, so our claim is that this ideal is generated by this element. And so again, this is really telling me I have multiple elements that I can choose as my generator. I just need to pick one that has the smallest degree that's not the zero polynomial. Okay, so we need to do double containment. One of the containments is pretty easy. Which containment would be easier to do? I is in this ideal, or this ideal is in I? That this ideal is in I. Because I already know G is in here, so every multiple of G also has to be in there. So I know that containment going in that direction, I get almost immediately here. Since G is in I get this containment by and really because I have an ideal, this is going to work. Right, because I know, actually this is only because of it being an ideal. Because I know if I take something in my ideal and something outside, it has to land back inside my ideal. So this is not by closure technically, but because I is an ideal. Okay, so now what we want to do is the reverse containment. Take something inside of I and show I can write it as a product of G times something else. Okay, so now we're going to let F be inside of our ideal. And again, our goal is to show it lands in here. The only way it lands in here is if it's G times something else. Okay, so this is where we're going to use our division algorithm. So here, we can use our division algorithm when the coefficients come from a field and where what you're dividing by is non-zero. So here, the thing that we're going to think about dividing by is our G, which we're assuming in this case is not equal to 0. So we can actually apply our division algorithm to think, what is F divided by G? Or how do I write F as a product of G plus some remainder? Okay, so here what we can say is that F is going to look like G times some other polynomial. And maybe here I'll put X's. Doesn't actually matter. Plus my remainder, where I have some more information, where I know Q and R are in my polynomial ring. And I have information about R as well in terms of its degree. And so I know either R is the zero polynomial or the degree of R is less than what? What do I compare my remainder to? Do I compare it to F or do I compare it to G? To G, the thing that you think of dividing by, right? If it was a bigger degree, really I could have kept dividing. I didn't go all the way through. So here, either my remainder is the zero polynomial, or I get back a degree that's smaller than G. Okay, those are my only two options, right? And it'd be great if this was equal to 0, because now I showed F is a multiple of G, and so F isn't the correct ideal. So really the thing that we want to study is, why can't this be true? Why can't the degree of R be less than the degree of G? It's something that we can remember is G is going to be some polynomial in I that has the smallest degree. So if I can show R is inside my ideal, then this can't be true, because it can't be less than the degree of G unless it was the zero polynomial itself. Okay, so the thing that we'll study is R, so we'll manipulate our equation so that we see what R is equal to, and we'll be able to show that it has to land in the ideal, and so that this is not possible. So if this was true, we'd be good. If this one was true, something would go wrong. Okay, but here we can write R by subtracting the G times Q on both sides. Okay, and this is in my ideal. This is in my ideal, and then this is inside of my quotient ring, or excuse me, my polynomial ring. Okay, but because I have an ideal, if I take something on the inside, something on the outside, I know it'll land on the inside. And because it's an ideal, it's made closed under addition and subtraction. And so I know this whole thing is inside of I. Oh. Yep, I did want to show I. All right, so this is telling me I have something in my ideal. Either it's the zero polynomial or it has degree less than G, but this is impossible, right? So this has to have degree 0. But the degree of G is minimal. And so R has to be the zero polynomial, which means F can be written as G times Q, or Q is something in your polynomial ring. So F is an element of the ideal generated by G, and we just showed the reverse containment. Right? We took something from my ideal and showed that it landed in this specific principal ideal here. And so we really do get that these two are equal to each other. And really, I can take any polynomial I want with minimal degree, and it will generate my polynomial or my ideal here. Okay, so in our next class, we'll do just a little bit more on this and deciding, right, really exactly what we were doing here is the statement of this theorem is I can generate I, this PID, using any minimal degree polynomial I want, as long as it's not 0, or if it was a 0 polynomial, right? Really the work that we did here was proving this statement here. But we'll just do one more example on this and then think about our chapter 17. So we'll start introducing our irreducible polynomials and things like that. But if there are no questions, then I'll see you guys tomorrow. Have a good one.